Let yourself settle in for a moment. Find that comfortable position where your body can truly relax, where the weight of the day begins to lift from your shoulders. Take a slow breath, feeling the air move through you. And as you exhale, let any tension drift away like smoke dispersing in the evening air. Tonight, we're embarking on a most unsettling discoveries the James Webb Space Telescope has ever made. A world that challenges everything we thought we knew about what planets can be and how they can exist. But don't worry about understanding every detail or remembering every number. Let the words wash over you, painting pictures in your mind of cosmic landscapes that stretch beyond imagination. This is a story about a planet that shouldn't exist, orbiting a star that defies comprehension. In conditions so extreme, they seem more like science fiction than science fact. So breathe, relax, and let's drift together into the depths of space, where something truly disturbing awaits our discovery. And before we begin this cosmic journey together, if you find comfort in these stories, in this blend of wonder and relaxation, please consider subscribing to The Science Pillow. Hit that like button to let us know you're here with us, exploring the universe from the comfort of wherever you find peace. Your support helps us continue bringing you these journeys through the cosmos, these explorations of the strange and wonderful that exist beyond our world. Now, let's discover what the James Webb Telescope has found lurking in the darkness. The discovery that changed everything. In December of 2025, astronomers staring at data from the James Webb Space Telescope experienced something that doesn't happen often in their field. Genuine shock. Not the excitement of finding something interesting, not the satisfaction of confirming a hypothesis, but true, profound surprise at discovering something that fundamentally doesn't make sense. They were looking at a planet designated PSR J2322-265 Zerab, located approximately 750 light-years away from Earth, in the constellation Sculptor, and what they saw defied every model, every theory, every expectation they had developed over decades of studying planets. Michael Zhang, an astronomer at the University of Chicago and the principal investigator of the study, remembers the moment with crystalline clarity. "I remember after we got the data down," he said, "our collective reaction was, what the heck is this? It's extremely different from what we expected." Peter Gao, a member of the research team from the Carnegie Earth and Planets Laboratory, echoed this sentiment with equal bewilderment. "This was an absolute surprise," he stated simply, as if those words could somehow encapsulate the enormity of what they were seeing. The planet itself exists in a system that represents one of the most extreme environments imaginable in our universe. PSR J2322-265 Zerob has roughly the mass of Jupiter, one of the gas giants in our own solar system. But there, the similarities end abruptly and completely. This world orbits not a normal star like our sun, but a pulsar, a rapidly spinning neutron star, the crushed remnant of a massive star that died in one of the most violent events the universe can produce. The pulsar, at the center of this system, spins approximately 300 times every second, completing 18,000 rotations every minute. Each spin sending twin beams of gamma radiation and high-energy particles screaming out into space like a cosmic lighthouse gone mad. The distance between this planet and its dead star host is minuscule, barely comprehensible when we try to relate it to our own solar system. PSR J2322-265 Zerob orbits just 1 million miles from its pulsar, a distance that sounds vast until you realize that Mercury, the closest planet to our sun, orbits at about 36 million miles. Earth sits 93 million miles from the Sun. This planet orbits more than 90 times closer to its star than Earth does to the Sun, and 36 times closer than Mercury. At this proximity, the planet's entire year, the time it takes to complete one full orbit around its star, lasts exactly 7.8 hours. Think about that for a moment. Let that settle into your mind. While you sleep through a single night, this planet completes more than one full orbit around its star in the time it takes you to watch a movie, eat dinner, and settle in for the evening. This world has experienced dawn, noon, dusk, and midnight, and begun a new day. The very concept of seasons on such a world becomes meaningless. Weather patterns would be incomprehensible. The relentless, unending cycle of day and night, compressed into less than 8 hours, would create an environment so alien that our Earth-based intuitions simply cannot grasp it. But the orbital period, extreme as it is, represents only the beginning of this planet's strangeness. The intense gravitational forces from the much more massive pulsar have done something extraordinary to PSR J2322, 2650b. The planet is not spherical as we might expect planets to be. Instead, the tidal forces from its companion have stretched and distorted it into an ellipsoid shape, elongated, squeezed, transformed by gravity into something that resembles a lemon or a football more than a typical planet. The gravitational pull is so immense that the planet's equatorial diameter has been stretched to about 38% wider than its polar diameter. Imagine a world being constantly pulled and squeezed by forces so powerful that its very shape becomes distorted. The side of the planet facing the pulsar experiences gravitational forces vastly stronger than the far side, creating what scientists call tidal bulges. On Earth, we see a mild version of this effect in our ocean tides, caused by the moon's gravity. But on PSR J2322, 2650, the effect is so extreme that the entire planet, its rock, its interior, its very structure, has been reshaped by these relentless forces. The planet glows a dull red from the heat generated by this constant gravitational massage, like a piece of metal being repeatedly hammered on an anvil. The temperatures on this world exist in extremes that challenge our ability to conceptualize them. The side of the planet that perpetually faces the pulsar for PSR J2322, 2650 is tidally locked, showing the same face to its star at all times. Just as our moon shows only one face to Earth, experiences temperatures of approximately 3,700 degrees Fahrenheit, or about 2,038 degrees Celsius. This is hot enough to melt most known rocks, hot enough to vaporize many metals, hot enough that the very concept of a solid surface becomes questionable. But even more disturbing is the fact that this incredible temperature isn't caused primarily by the pulsar's light. No, the heat comes from something far more insidious. The pulsar itself emits mostly gamma rays and high-energy particles, radiation that is largely invisible in traditional wavelengths. These gamma rays slam into the planet's atmosphere with such ferocity that they heat it to temperatures far exceeding what the planet's distance from the star would normally produce. Scientists calculated that if the planet were heated only by the pulsar's starlight, temperatures would reach about 1300 Kelvin. But the actual temperature is approximately 1900 Kelvin, nearly 600 degrees hotter than expected, all because of the relentless bombardment of gamma radiation. The far side of the planet permanently facing away from the pulsar, remains relatively cooler at about 1200 degrees Fahrenheit, or 649 degrees Celsius. But cooler is a relative term here. Even the cold side of this world remains hot enough to melt lead, hot enough that no solid surface could exist in the way we understand it. The temperature differential between the two sides would create winds of unimaginable ferocity, atmospheric currents racing at speeds that would make Earth's most powerful hurricanes seem like gentle breezes. What makes PSR J232222650 particularly accessible to study, paradoxically, is the very thing that makes it so disturbing. Because the pulsar emits its energy primarily in gamma rays and other high-energy particles that the James Webb Space Telescope's infrared instruments cannot detect, astronomers can observe the planet in exquisite detail without the overwhelming glare of a normal star. Maya Belesne, a graduate student at Stanford University who worked on modeling the planet's geometry, explained the unusual advantage this provides. This system is unique, she noted, because we are able to view the planet illuminated by its host star, but not see the host star at all. So we get a really pristine spectrum, and we can better study this system in more detail than normal exoplanets. It's as if nature has provided astronomers with a laboratory experiment specifically designed to study an extreme planet without interference. The pulsar acts as a source of heat and radiation, affecting the planet in measurable ways, but remains essentially invisible to the instruments being used to observe it. This unique circumstance allowed the research team to capture data of unprecedented quality and detail, revealing aspects of the planet's atmosphere and behavior that would normally be impossible to discern. But what they found when they analyzed that pristine spectrum left them stunned, confused, and deeply sunsettled. Because PSR J232222650 doesn't just orbit in extreme conditions, it doesn't just have a distorted shape and hellish temperatures. What makes this planet truly disturbing? What elevates it from merely extreme to genuinely inexplicable is its atmosphere. And to understand why that atmosphere is so deeply troubling to scientists, we need to understand the stellar corpse at the center of this system, the pulsar itself, and the violent cosmic event that created it, the dead star at the center. To truly grasp the horror of PSR J232222650's existence, we must first understand its companion, the pulsar. PSR J232222650, the rapidly spinning stellar corpse around which this impossible planet orbits. Pulsars represent one of the most extreme states of matter in the universe, objects so dense and so strange that they challenge our everyday understanding of physics. They are the remnants of stellar death, the compressed hearts of stars that once burned with thermonuclear fire but met their end in one of the most violent events the cosmos can produce. The story of every pulsar begins with a massive star, one containing at least 8 to 10 times the mass of our Sun, burning steadily for millions of years through nuclear fusion. These stellar giants live fast and die young compared to smaller stars like our own Sun. While the Sun will burn for about 10 billion years in total, massive stars exhaust their nuclear fuel in just 10 to 20 million years. During their brief lifetimes, they burn through their hydrogen, then their helium, creating progressively heavier elements in their cores through a process called nucleosynthesis. As these massive stars age, they begin to resemble cosmic onions, with layers of different elements arranged in concentric shells. The outermost layers contain hydrogen and helium. Deeper in, we find shells of carbon and oxygen, then neon and magnesium, then silicon, and finally, at the very center, iron. Each shell burns at progressively higher temperatures, fusing lighter elements into heavier ones, releasing energy that fights against gravity's relentless inward pull. But when the core begins to produce iron, something changes. Iron is special. It sits at the peak of the binding energy curve, meaning that fusing iron into heavier elements doesn't release energy. It consumes energy. When a massive star's core fills with iron, nuclear fusion can no longer provide the outward pressure needed to counteract gravity. The core, now containing roughly 1.4 solar masses of iron, compressed into a sphere about the size of Earth, suddenly finds itself without support. And then, in a fraction of a second, catastrophe strikes. The iron core collapses, not slowly, not gradually, but at speeds approaching 1/4 the speed of light. In less than a second, a sphere the size of Earth, containing more mass than our entire sun, collapses down to a size of about 10 to 20 kilometers, roughly the size of a large city. The collapse is so rapid, so catastrophic, that the iron atoms themselves cannot withstand it under pressures and densities that exceed anything found elsewhere in the universe. The electron clouds surrounding atomic nuclei are crushed into the nuclei themselves. Electrons, which normally orbit atomic nuclei at discrete distances, are forced to combine with protons in a process called inverse beta decay, creating neutrons and neutrinos. The neutrinos, ghostly particles that barely interact with matter, stream outward in numbers beyond imagination. A single supernova produces more neutrinos in a few seconds than all the stars in the visible universe produce in the same time span. Meanwhile, the core continues its collapse until the neutrons themselves, packed more tightly than atomic nuclei, begin to exert what physicists call neutron degeneracy pressure. This quantum mechanical effect, arising from the Pauli exclusion principle, which states that no two identical fermions can occupy the same quantum state, finally halts the collapse. The core rebounds, stiffening suddenly, and the outer layers of the star, which had been falling inward at tremendous speeds, slam into this newly formed neutron core and bounce. The result is a supernova explosion, one of the most luminous events in the universe. For a brief time, a single supernova can outshine an entire galaxy containing hundreds of billions of stars. The explosion hurls the star's outer layers into space at speeds exceeding 10% of the speed of light, enriching the interstellar medium with heavy elements forged in the star's core and, in the explosion itself, elements heavier than iron. Gold, platinum, uranium, and many others are created in these violent moments and scattered across space, eventually becoming part of new generations of stars and planets. Every atom of gold and every piece of jewelry, every atom of iodine in your thyroid, every atom of uranium in nuclear reactors was created in supernova explosions billions of years ago. But at the heart of this violence, something extraordinary remains. A neutron star. This object represents matter in one of its most extreme possible forms. A typical neutron star contains about 1.4 times the mass of our Sun, about 330,000 times the mass of Earth, compressed into a sphere with a radius of only 10 to 12 kilometers. To put this in perspective, imagine taking all of Mount Everest and compressing it into a volume smaller than a sugar cube. A teaspoon of neutron star material would weigh approximately 1 billion tons on Earth. roughly the same as all of humanity combined. The density of a neutron star approaches and even exceeds nuclear density, the density of matter inside atomic nuclei. In some sense, a neutron star is like a single atomic nucleus, but one containing an unimaginable number of neutrons. The interior structure of neutron stars remains one of the great mysteries in physics. At such extreme densities, matter may exist in exotic forms that cannot be created in any laboratory. Some theories suggest that the cores of the most massive neutron stars might contain quarks, the fundamental particles that make up neutrons and protons, existing freely rather than bound inside nuclear particles. Others propose the existence of strange forms of matter, such as hyperons or pion condensates, states of matter so exotic that physicists can barely describe them mathematically. The surface of a neutron star, if you could somehow stand on it without being instantly crushed, would present a landscape unlike anything in the universe. Gravity at the surface of a typical neutron star is approximately 200 billion times stronger than Earth's gravity. If you could magically survive long enough to drop a marshmallow onto a neutron star's surface, it would hit with the force of a nuclear bomb. The escape velocity, the speed needed to escape the neutron star's gravitational pull, is approximately half the speed of light. The crust of a neutron star is thought to be made of crystallized iron nuclei arranged in a lattice. But iron, unlike any found on Earth, under the extreme pressures, the lattice structure becomes so strong that it's billions of times harder than steel. But neutron stars are not just extraordinarily dense, they are also extraordinarily magnetic. When the core of the original star collapsed, it retained its magnetic field. But because the field lines were compressed, along with the star's material, the magnetic field strength increased by factors of trillions. A typical neutron star has a magnetic field about 1 trillion times stronger than Earth's magnetic field. Some neutron stars, called magnetars, have fields another 1,000 times stronger still, making them the most magnetic objects known to exist in the universe. And then there's the rotation. Just as an ice skater spins faster when pulling their arms inward due to conservation of angular momentum, a collapsing stellar core spins faster as it shrinks. The original star might have rotated once every few weeks. The resulting neutron star can rotate hundreds of times per second. The fastest known pulsar, designated PSR Joan 748 2446 AD, spins 716 times every second. Over 700 complete rotations in the time it takes you to blink your eyes. At this rotation rate, the surface of the neutron star at its equator is moving at approximately 1/4 the speed of light. It's this rotation, combined with the intense magnetic field, that creates the phenomenon we call a pulsar. The neutron star's magnetic field is not aligned with its rotational axis. The magnetic poles don't coincide with the geographic poles. As the neutron star rotates, its magnetic field rotates with it. Charged particles near the neutron star get caught in the magnetic field and are accelerated to tremendous speeds, creating beams of electromagnetic radiation that stream out from the magnetic poles. These beams sweep through space like the beam from a lighthouse as the neutron star rotates. If Earth happens to lie in the path of one of these beams, we detect a pulse of radiation each time the beam sweeps past us. It's like standing on a rocky coast and watching a distant lighthouse beam sweep across the water. We see a flash each time the beam points in our direction. The regularity of these pulses can be astounding. The Crab pulsar, located in the Crab Nebula and formed during a supernova observed by Chinese astronomers in the year 1054. Pulses exactly 30 times per second with a regularity that rivals atomic clocks. Some millisecond pulsars are even more regular, serving as some of the most precise timekeepers in the universe. PSR J2322 2650, the pulsar at the center of our disturbing system, is one of these millisecond pulsars. It spins approximately 300 times per second, or once every 3.46 milliseconds. This classification millisecond pulsar indicates that it has been recycled through a process involving a companion star. Young pulsars, freshly formed from supernova explosions, typically spin slower, perhaps once. They gradually slow down over millions of years as they lose rotational energy through the emission of electromagnetic radiation and high-energy particles. But sometimes a pulsar exists in a binary system with a companion star. If matter from that companion star falls onto the neutron star, a process called accretion, it can spin the pulsar back up to incredibly fast rotation rates. The process works like a cosmic merry-go-round. As matter from the companion spirals onto the neutron star, it carries angular momentum with it, gradually spinning the neutron star faster and faster, sometimes reaching rotation rates of hundreds or even 1,000 times per second. At the same time, the accretion process tends to reduce the neutron star's magnetic field strength, creating what astronomers call recycled millisecond pulsars. This brings us to one of the most disturbing aspects of PSR J2322 2650 and its planetary companion. The system appears to be what astronomers call a black widow pulsar system, named after the spider species, where the female sometimes consumes the male after mating. In these cosmic black widow systems, the pulsar, having been spun up by accreting material from a companion, then turns on its benefactor, blasting it with powerful winds of high-energy particles and intense radiation. Over millions to billions of years, this relentless bombardment gradually erodes the companion, carving away its outer layers and ejecting them into space, ultimately consuming the very star that gave the pulsar its incredible rotation rate. Black widow systems typically contain a neutron star paired with a very low-mass companion, usually less than. The pulsar's radiation and particle wind heat the side of the companion facing it to temperatures far exceeding what the star's own internal fusion could achieve. As the companion orbits the pulsar, we see it alternately brighten and dim. Bright when its heated side faces Earth, dim when its cooler side rotates into view. All the while, the pulsar is gradually evaporating this companion, blowing it away into space, atom by atom, destroying the very star that gave it new life. PSR J2322 2650 Robe appears to be the companion in such a system, though with a crucial difference that makes it even more mysterious. Traditional black widow systems have stellar companions. Small stars, but stars nonetheless, objects that generate energy through nuclear fusion. PSR J2322 2650 Robe, despite having roughly the mass of Jupiter, is officially classified as a planet, not a star. It doesn't generate energy through fusion. It's not massive enough for that. Yet, it exists in the same configuration as a black widow companion, being slowly cooked and potentially evaporated by its pulsar host. Roger Ramani, a professor at Stanford and one of the world's leading experts on black widow systems, noted the peculiarity of this classification. The International Astronomical Union defines this object as an exoplanet, not a star, based on its mass and formation mechanism. But its behavior and its fate seem to mirror those of black widow companions. "Did this thing form like a normal planet?" asked Michael Zhang rhetorically. "No, because the composition is entirely different." "Did it form by stripping the outside of a star, like normal black widow systems are formed?" "Probably not, because nuclear physics does not make pure carbon." And here we arrive at the heart of what makes PSR J2322265 Zerob so profoundly disturbing. Because when astronomers used the James Webb Space Telescope to analyze the light from this planet, to understand what its atmosphere contains and how it behaves, they found something that, according to every model and theory they've developed, simply cannot exist. They found an atmosphere so bizarre, so fundamentally wrong, that it challenges our understanding of planetary formation, atmospheric chemistry, and the very nature of what planets can be. An atmosphere that defies physics. When the James Webb Space Telescope's instruments analyzed the spectrum of light coming from PSR J232222650b, the precise fingerprints of atoms and molecules absorbing and emitting radiation at specific wavelengths, the research team expected to see familiar signatures based on decades of studying planets. Both in our solar system and beyond, astronomers have developed a strong understanding of what planetary atmospheres typically contain. They expected to see water vapor, or methane, or carbon dioxide, or perhaps ammonia, molecules that appear in the atmospheres of countless worlds we've observed. Instead, they saw something that left them stunned. Instead of finding the normal molecules we expect to see on an exoplanet, Michael Zhang explained, like water, methane, and carbon dioxide, we saw molecular carbon, specifically C3 and C2. Let that sink in for a moment. The atmosphere of this planet is dominated not by the molecules we see everywhere else, not by compounds that form naturally through chemical processes we understand, but by pure molecular carbon, carbon atoms bonded directly to other carbon atoms in short chains. Diatomic carbon, C2, two carbon atoms bonded together, is an extremely reactive molecule. Triatomic carbon, C3, three carbon atoms in a chain, is even more unusual. These molecules exist in some of the hottest environments in the universe. In the outer atmospheres of carbon-rich stars, in the plasma of electric arcs, in flames, and in laboratory conditions where researchers deliberately create them for study. But they should not, under any reasonable atmospheric chemistry model, dominate the atmosphere of a planet. They should react with other elements, form more stable compounds, or break down under radiation. Yet here they are, floating through the atmosphere of PSR J2322265 Zerob in quantities so large that they define the planet's atmospheric composition. The atmosphere also contains substantial amounts of helium, the second lightest element in the universe. This creates a bizarre cocktail of helium and carbon molecules, with almost no detectable amounts of oxygen, nitrogen, water vapor, methane, carbon dioxide, or any of the other compounds that make up planetary atmospheres throughout the cosmos. Think about that for a moment. Earth's atmosphere is 78% nitrogen and 21% oxygen. Venus has an atmosphere of 96% carbon dioxide. Mars is 95% carbon dioxide. Jupiter and Saturn are dominated by hydrogen and helium. Uranus and Neptune have atmospheres of hydrogen, helium, and methane. Every planet we've studied in detail has an atmosphere dominated by simple, stable compounds. PSR J2322265 265 Zerobe has an atmosphere of helium and pure molecular carbon, with virtually no oxygen or nitrogen detected at all. This absence is crucial. C2 and C3 molecules can only remain abundant if there's almost no oxygen or nitrogen present. Even tiny amounts of these elements would react with the carbon, forming more stable compounds like carbon monoxide, carbon dioxide, or cyanide. The fact that astronomers see C2 and C3 in such abundance tells them something extraordinary. This atmosphere lacks the basic building blocks that appear in virtually every other atmosphere in the known universe. The atmosphere's carbon doesn't just float there invisibly. Under the extreme conditions on PSR J2322, 265 Zerobe, this carbon forms clouds. Not clouds of water vapor like on Earth, not clouds of sulfuric acid like on Venus, but clouds of carbon soot. Imagine an atmosphere filled with fine particles of carbon, the same substance that makes up coal, charcoal, and the lead in pencils, floating in wispy formations across an alien sky glowing red from the heat of a dead star's radiation. These soot clouds would create an atmospheric haze unlike anything we've ever observed, a dark shroud that absorbs some wavelengths of light while scattering others, giving the planet an appearance that defies description. But the story gets even more extraordinary when we consider what happens deeper in the planet's atmosphere and interior. Carbon under normal pressures exists as graphite or diamond, depending on how it's arranged. At Earth's surface, graphite is the stable form. It's what we find in nature. Diamond requires tremendous pressure to form, which is why natural diamonds are found only deep underground or in specific geological contexts where they've been brought to the surface through volcanic activity. On PSR J232265, Zerobe, the pressure deep in the atmosphere and beneath it is enormous. The planet has roughly Jupiter's mass compressed into a smaller volume, and the gravitational pressure at depth would be crushing beyond imagination. Under these conditions, Roger Romani and other researchers theorize the carbon in the atmosphere could condense as it sinks deeper, eventually forming diamonds. Not diamonds like those in jewelry stores. Small, crystalline, perfectly formed, but possibly enormous crystals or layers of diamond, created continuously as carbon from the soot clouds above precipitates downward into regions of higher pressure. Picture it, an atmosphere of helium laced with molecular carbon forming soot clouds that occasionally rain downward, the particles sinking through progressively denser layers, compressed by ever-increasing pressure until the carbon atoms reorganize themselves into the crystalline structure of diamond. Diamond rain falling through an alien sky, accumulating in layers beneath the atmosphere, creating perhaps a shell of diamond surrounding the planet's interior. It sounds like something from a fantasy novel, but it may be the reality on this deeply strange world. As the companion cools down, Romani theorized, the mixture of carbon and oxygen in the interior starts to crystallize. This crystallization process might be ongoing, with carbon and potentially oxygen forming solid layers deep within the planet. But the question remains, where did all this carbon come from in the first place? And more importantly, where did all the oxygen and nitrogen go? Peter Gao, the researcher who expressed such surprise at the atmospheric composition, pointed out the fundamental challenge this planet presents. It's very hard to imagine how you get this extremely carbon-enriched composition, he said. It seems to rule out every known formation mechanism. Every known mechanism. Consider what that means. Astronomers have developed detailed models for how planets form. From the dust and gas in protoplanetary disks around young stars through gradual accumulation of material, through gas capture, and atmospheric evolution. These models have been tested against thousands of exoplanets discovered over the past 30 years, and while they've been refined and adjusted, they've held up remarkably well. But PSR J2322265 ZeROB doesn't fit any of these models. If it formed like a normal planet from a disk of gas and dust, its atmosphere should reflect the composition of that disk. The universe is dominated by hydrogen and helium, with traces of heavier elements. A planet forming normally should capture primarily hydrogen and helium, with small amounts of carbon, oxygen, nitrogen, and other elements. We see this pattern in Jupiter, Saturn, and countless exoplanets. But PSR J2322265 ZeROB has helium, yes, but instead of hydrogen, it has molecular carbon. And instead of compounds containing the abundant elements oxygen and nitrogen, it has none. Could the planet have formed from the leftover material of a star that was stripped away in the Black Widow process? This is one hypothesis researchers considered. If PSR J2322265 ZeROB formed from material blown off a companion star, as the pulsar's radiation eroded it, the composition might reflect nuclear fusion products from that star's core. But nuclear fusion in stars produces carbon, yes, but it also produces oxygen in similar or even greater quantities. The fusion process that turns helium into carbon also creates oxygen as a byproduct. A planet formed from stellar material should have both carbon and oxygen in abundance, not just carbon. Some researchers speculated about exotic formation scenarios. Perhaps PSR J2322265 ZeROB represents the stripped core of a larger planet, with all its hydrogen and helium atmosphere blown away by the pulsar's radiation, leaving behind only a carbon-rich interior. But even this doesn't quite work. Planetary cores typically contain iron and silicate rocks, not pure carbon. And if the atmosphere were stripped away entirely, how did the planet retain or reaccumulate the helium and carbon atmosphere we now observe? Another possibility involves the unique chemistry of the system. The pulsar's intense gamma radiation doesn't just heat the atmosphere, it ionizes it, breaking molecules apart and allowing unusual chemistry to occur. Perhaps this radiation preferentially destroys certain molecules while leaving others intact. Maybe oxygen and nitrogen compounds are continuously broken down by the radiation, while carbon molecules, for some reason, survive. But physicists working on the problem have struggled to find a mechanism that would produce this effect. The radiation should, if anything, break down molecular carbon as efficiently as it breaks down other compounds. What makes the situation even more puzzling is the planet's atmosphere behavior. Not only is the composition wrong, but the atmosphere itself is doing something deeply strange. Based on the planet's brightness variations, as it orbits the pulsar, researchers have determined that the atmosphere is rotating westward in the opposite direction to the planet's rotation. The planet itself is tidally locked, spinning eastward on its axis exactly once per orbit, keeping the same face pointed at the pulsar, just as our moon shows only one face to Earth. But the atmosphere has detached from the surface and is racing westward at tremendous speeds, driven by forces that aren't entirely understood. This retrograde atmospheric rotation creates winds of extraordinary ferocity. The atmosphere is being heated asymmetrically. The side facing the pulsar receives a tremendous onslaught of gamma radiation, while the far side remains in relative darkness. This temperature difference drives powerful currents, But the physics of how these currents produce a westward superrotation remains a topic of intense research. We see similar effects on Venus, where the atmosphere rotates much faster than the planet itself, but the mechanisms at work on PSR, J23222650 are far more extreme. The temperature of the atmosphere, heated by gamma radiation to approximately 1900 Kelvin, about 1600 degrees Celsius, is far hotter than the star's infrared emission alone could produce. The gamma rays, with their immense energies, transfer heat to the atmosphere with brutal efficiency. This creates a thermal environment unlike anything observed elsewhere. The atmosphere exists in a state of constant turmoil, roiled by temperature gradients, blasted by radiation, rotating in a direction opposite to the planet's spin, filled with soot clouds and possibly precipitation of diamonds. And underlying all of this is a disturbing realization. This planet is being slowly destroyed. The pulsar's radiation isn't just heating the atmosphere and creating its bizarre chemistry. It's gradually evaporating the planet itself, stripping away its outer layers atom by atom, molecule by molecule, carrying them off into space on particle winds. The process is slow. It might take billions of years to completely consume the planet, but it's inexorable. PSR J23222650 is not in a stable state. It's in the process of dying, being slowly cooked and evaporated by its stellar companion, destined eventually to be reduced to nothing more than a stream of particles spiraling into the pulsar. This fate is shared by many objects in Black Widow systems, but the uniqueness of PSR J23222650's composition and atmospheric chemistry makes its slow death particularly fascinating and disturbing to astronomers. Watching a world with such an inexplicable atmosphere gradually dissipate into space provides a natural laboratory for studying extreme atmospheric processes and planetary evolution under conditions that push the boundaries of physics and chemistry. Maya Belesne, who worked on modeling the planet's shape and orbital geometry, noted that the system's unique properties allowed for unprecedented observational clarity. But she and her colleagues are keenly aware that what they're seeing is a snapshot in time of an object that challenges fundamental theories. We get a really pristine spectrum, she explained, and we can better study this system in more detail than normal exoplanets. But that detailed study has revealed a world that seems to violate the rules by which planets should exist. Black Widow systems, when dead stars devour their companions. To understand why PSR J23222650 exists in such a disturbing state, we need to explore the broader category of systems to which it belongs, the Black Widows and their related cousins, the Redbacks and Tidarans. These systems, named after species of spiders where the female consumes the male, represent some of the most dramatic and destructive stellar relationships in the universe. They show us that, even in death, stars can be violent, voracious, and utterly ruthless in their treatment of nearby companions. The first Black Widow pulsar was discovered in 1988, designated PSR B1957+20, located roughly 6,500 light-years from Earth. Astronomers noticed something peculiar about this millisecond pulsar, something that had never been observed before. The pulsar's radio signals, normally remarkably regular and predictable, were being periodically eclipsed, blocked by something passing between the pulsar and Earth. But what could eclipse a pulsar? The neutron star itself is tiny, barely 12 kilometers across, and its radio beams shoot out from its magnetic poles. For something to block those beams, it would have to pass very close to the neutron star, and it would have to contain enough material to absorb or scatter the radio waves. Detailed observations revealed that PSRB 1957 plus 20 has a companion, a small object with a mass only about 2% that of the Sun, roughly 20 times the mass of Jupiter, orbiting the pulsar every 9.2 hours. This companion, probably a brown dwarf or the stripped remnant of a once larger star, sits in an extraordinarily tight orbit around the pulsar, and the pulsar is destroying it. The process works like this. The pulsar, spinning over 600 times per second, generates powerful winds of high-energy particles and intense magnetic fields. These winds, combined with the pulsar's gamma and X-ray radiation, slam into the facing side of the companion with tremendous energy. The radiation and particle bombardment heat the companion's surface to temperatures far exceeding those that the object's mass and internal structure would normally produce. On PSRB 1957 plus 20's companion, the side facing the pulsar heats to temperatures around 12,000 degrees Fahrenheit, more than twice as hot as the Sun's surface, while the far side remains much cooler. This intense asymmetric heating does more than just create temperature differences. It actively evaporates the companion. Material from the heated hemisphere is blown off into space, creating a stream of ions and electrons that flows outward from the system. It's this stream of ionized material that causes the eclipses of the pulsar's radio signal. When Earth's line of sight to the pulsar passes through this cloud of evaporating material, the radio waves scatter and disperse, and we temporarily lose the pulsar signal. The name Black Widow was applied to this system because of the apparent parallels to the spider species, where the female sometimes consumes the male after mating. In the cosmic version, the pulsar, having been spun up to millisecond periods by accreting material from the companion, then turns on its benefactor and slowly consumes it. The irony is stark. The companion star donated material to the neutron star, spinning it up and giving it the rotational energy it now has, and in return, the neutron star is gradually destroying the companion, evaporating it away into space. Since the discovery of the first Black Widow, astronomers have found dozens more of these systems, enough to recognize patterns and categorize them into subcategories. Black Widow systems proper have companions with very low masses, typically less than 0.05 solar masses, less than 5% the mass of the Sun. These companions are often difficult to detect through optical telescopes because they're small and relatively faint, though the heated side facing the pulsar can glow brightly enough to be observed. Redback systems, named after an Australian relative of Black Widow spiders, have slightly more massive companions, typically between 0.1 and 1 solar masses. These companions are more substantial, often still undergoing nuclear fusion in their cores, making them true stars rather than stellar remnants or brown dwarfs. But they too are being cooked by their pulsar companions, with the facing hemisphere heated to extraordinary temperatures. And then there are the tide herons, named after a spider species where the male is exceptionally tiny compared to the female about 1% of her size. In Tidaran pulsar systems, the companion has extraordinarily low mass, around 1/100th of a solar mass, or even less. These systems represent perhaps the final stage of Black Widow evolution, where the companion has been eroded down to almost nothing, a mere wisp of material still orbiting the pulsar. PSR J2 2265. Zerob fits awkwardly into this classification scheme. Its mass, roughly that of Jupiter, about 1,000th the mass of the Sun, places it far below even the Tidarans. In terms of mass, it's more like a planet than a star or stellar remnant. The International Astronomical Union's definition of a planet versus a brown dwarf versus a star is based partly on mass and partly on formation mechanism. PSR J2322265 Zerob, despite its bizarre properties, is officially classified as an exoplanet, making it one of the very few planets known to orbit a pulsar. But the classification raises profound questions. Did PSR J2322265 Zerob form as a planet, accumulating from a disk of material around the pulsar? This seems unlikely. Pulsars are born in supernova explosions, which should destroy or disperse any planetary disk that existed around the progenitor star. Or did it form as a larger object, perhaps a low-mass star or brown dwarf, and then get eroded down to its current mass by the pulsar's radiation? This would explain why it exists in a black widow configuration, but it makes the atmospheric composition even more puzzling. There are only a handful of known planets orbiting pulsars. The first planets ever discovered beyond our solar system were actually pulsar planets, found in 1990, two orbiting PSR B1257 plus 12. These planets, named Poltergeist and Phobator, along with a third planet called Draugr, were detected not through direct observations, but through subtle variations in the timing of the pulsar's radio pulses. The planet's gravitational pull causes the pulsar to wobble slightly as it moves through space, and this wobble produces tiny but measurable changes in when the radio pulses arrive at Earth. The PSRB 1257 plus 12 system contains 3 confirmed planets, with masses ranging from twice the Moon's mass to about 4 times Earth's mass. How these planets formed remains uncertain. They could be the remnants of planets that somehow survived the supernova that created the pulsar, though the intense radiation and blast wave from the supernova should have vaporized any planets in the system. Or they could have formed from a debris disk after the supernova, accreting from material that fell back toward the neutron star. Or they might represent the remains of a companion star that was shredded by the pulsar's tidal forces and radiation. PSR J2322265 Zerob represents a different scenario entirely. Rather than orbiting at a safe distance like the PSR B1257 plus 12 planets, it sits in the destructive embrace of a black widow system, being actively cooked and unlike the PSR B1257 plus 12 planets, which are too far away and too small for detailed atmospheric study, PSR J2322265 Zerob is close enough and large enough that the James Webb Space Telescope can analyze its atmosphere in detail, revealing the bizarre carbon-helium composition that has left astronomers so bewildered. Alice Harding, an astrophysicist at NASA's Goddard Space Flight Center, has studied spider pulsar systems extensively. She explains the destructive process in stark terms. The high-energy emission and wind from the pulsar basically heats and blows off the normal star's material, and over millions to billions of years can eat away the entire star. These systems can completely consume their companion stars, and that's how we think solitary millisecond pulsars form. The universe contains many millisecond pulsars that appear to be solitary, spinning rapidly in isolation with no companion visible nearby. Based on the physics of pulsar spin-up, these solitary millisecond pulsars should have companions. Something must have spun them up to such rapid rotation rates. Black widow systems provide the answer. The companions once existed, but have been completely evaporated, consumed by the pulsars they helped create. The solitary millisecond pulsars we see today are the final stage of this process, the survivors standing alone over the scattered atoms of their former companions. PSR J2322-265 Zerob, then, is not in a stable configuration. It's in the process of being destroyed. Over the coming millions or billions of years, assuming no other factors intervene, the pulsar's radiation will continue to strip away the planet's atmosphere, layer by layer. The soot clouds will be blown into space. The diamond rain will slow and cease as the carbon source diminishes. Eventually, the atmosphere will be gone entirely, stripped down to whatever lies beneath. If anything lies beneath, the planet might be reduced to a bare core, a dense ball of exotic material still orbiting the pulsar, or it might be completely dissipated, reduced to a thin stream of particles, spiraling into the neutron star. The timescale for this destruction depends on many factors: the intensity of the pulsar's radiation and particle wind, the composition and structure of the planet, the efficiency of the evaporation process. Some black widow companions have been evaporating for millions of years and still retain substantial mass. Others appear to be in their final stages, reduced to wisps barely detectable. PSR J2322-265 Zerob, with its substantial Jupiter-like mass, might survive for a considerable time yet, but its fate is sealed. What makes the system particularly valuable for research is that it provides a real-time laboratory for studying atmospheric evaporation under extreme conditions. On Earth, we've studied how planets lose their atmospheres through processes like James escape, where individual molecules gain enough thermal energy to escape a planet's gravity, or through stripping by solar wind, where charged particles from the sun gradually erode the upper atmosphere. Mars probably lost much of its atmosphere through such processes billions of years ago, when its magnetic field disappeared. The Martian example is instructive. 4 billion years ago, Mars had a much thicker atmosphere, possibly thick enough to allow liquid water to exist on its surface. Evidence for ancient river valleys, lake beds, and possible ocean basins suggests that Mars was once a much wetter, warmer world. But Mars is smaller than Earth, with weaker gravity, and at some point early in its history, its magnetic field shut down. Without this protective magnetic shield, the solar wind began stripping away the atmosphere. Over billions of years, Mars lost most of its air, becoming the cold, dry desert world we see today. But the atmospheric loss on Mars occurred slowly over geological timescales. PSR J2322-265 Zerob is experiencing something far more violent and rapid. The pulsar's radiation is millions of times more intense than the solar wind that eroded Mars's atmosphere. The process isn't a gentle leakage over billions of years. It's an active blasting away of the planet's outer layers. If we could somehow watch PSR J2322-265 Zerob over millions of years, we might see measurable changes in its mass, its atmospheric density, even its orbital parameters as material is stripped away and the gravitational dynamics shift. But the evaporation occurring on PSR J2322-265 Zerob is far more violent and dramatic. The pulsar's gamma radiation and particle winds don't gently coax molecules away, they blast them off with brutal efficiency. This provides insights into atmospheric processes in extreme environments. that we could never study in our own solar system. It also raises questions about the limits of planetary survival. Under what conditions can a planet maintain an atmosphere? How quickly does evaporation occur under various radiation intensities? What factors determine whether a planet retains a thin shell or is stripped entirely? For PSR J23222650 Zerob specifically, one of the most pressing mysteries is whether the carbon-helium atmosphere we observe is being continuously replenished from the planet's interior, or whether it's a finite reservoir gradually being depleted. If the atmosphere is being replenished, if gases are continuously bubbling up from deeper layers or being released from the planet's interior through some process, then the planet might maintain its bizarre atmospheric composition for an extended period. But if the atmosphere is simply being stripped away without replenishment, then we might be witnessing a transitional phase, and the atmospheric composition could change dramatically over time. Roger Romani, the Stanford researcher who has studied black widow systems for years, sees PSR J2322265 Zerob as a unique window into processes we can barely imagine. The system combines the extreme conditions of a black widow with the unusual circumstance of having a planetary mass object instead of a stellar remnant, all while displaying atmospheric chemistry that defies explanation. It's a natural experiment in exotic physics and chemistry, and astronomers are eager to continue observing it, watching how the atmosphere evolves, measuring how quickly material is being lost, and trying to understand the fundamental processes that created and maintain this impossible world. But PSR J2322265 Zerob is not alone in defying expectations. While it may be the most disturbing planet the James Webb Telescope has found, it's part of a broader pattern of discoveries that are forcing astronomers to rethink everything they thought they knew about what planets can be and how they can exist. Across the universe, other worlds are challenging our theories in equally fundamental ways, creating a cosmic menagerie of impossibility. The formation mystery: how could this exist? The existence of PSR J2322265 Zerob presents a profound puzzle that cuts to the heart of planetary science. Every model astronomers have developed for how planets form and evolve suggests that this object cannot exist. Yet, there it is, 750 light-years away, stubbornly real, spinning around its pulsar companion every 7.8 hours, with an atmosphere that defies explanation. The challenge facing researchers isn't just to explain one or two unusual features, it's to explain how everything about this planet came to be. Let's start with the most fundamental question. Where did PSR J2322265 Zerob come from? There are essentially three possibilities, each with serious problems. The first possibility is that PSR J2322265 Zerob formed as a normal planet would from a disk of gas and dust around the pulsar. After all, we know that pulsars can have planets. The PSR B1257 plus 12 system contains 3 of them. Perhaps the supernova that created PSR J2322650 left behind enough material that some fell back toward the neutron star, forming an accretion disk. Over time, this disk could have coalesced into planets through the same processes that form planets around normal stars: dust grains sticking together, growing into pebbles, pebbles into boulders, boulders into planetesimals, and eventually planets. But this scenario faces immediate challenges. First, the composition is wrong. If PSR J2322265 Zerob formed from supernova fallback material, It should reflect the composition of the exploded star's outer layers. Supernovae produce and scatter heavy elements, but they produce them in specific ratios. Carbon is created in abundance, yes, but so is oxygen. In fact, more oxygen than carbon typically. A planet forming from supernova debris should have both elements. Yet PSR J2322265 Zerob has carbon and helium with virtually no detectable oxygen. Second, the orbital distance is problematic. PSR J2322265 Zerob orbits just 1 million miles from the pulsar, extremely close in astronomical terms. For a planet to form at this distance from an accretion disk would require the disk to be very hot and very dense. Material this close to a neutron star would be moving at tremendous speeds, orbiting once every few hours. The physical conditions would make it difficult for solid particles to coalesce. They'd be colliding at such high velocities that impacts would tend to shatter rather than stick. The second possibility is that PSR J2322265 Zerob started life as something else, perhaps a low-mass star or a brown dwarf, and was then eroded down to its current planetary mass by the pulsar's radiation. This would explain why it exists in a black widow configuration. The object could have originally been massive enough to spin up the pulsar through mass transfer, and then the pulsar's radiation could have evaporated away most of the companion's mass, leaving only the core. This scenario is more promising in some ways. Black widow systems work this way. Companions are eroded over time. But again, the composition presents severe difficulties. If PSR J2322265 Zerob is the stripped core of a former star, what are we looking at? Stellar cores contain the products of nuclear fusion. A star massive enough to have been the pulsar's companion would have fused hydrogen into helium in its outer regions and possibly created heavier elements deeper in. But the fusion process that creates carbon also creates oxygen and nitrogen. There's no known nuclear fusion process that produces primarily carbon while excluding oxygen and nitrogen. Perhaps PSR J2322265 Zerob represents not the fusion-generated core of a star, but some other component. Could it be the remnant of a brown dwarf that never achieved fusion? Brown dwarfs, objects too small to sustain hydrogen fusion, have compositions more similar to planets than stars. But brown dwarfs form from collapsing clouds of gas and should have compositions reflecting the interstellar medium from which they formed, primarily hydrogen and helium, with traces of heavier elements. We don't see hydrogen on PSR J2322265 Zerob, and the carbon-to-helium ratio is completely wrong for a brown dwarf. The third possibility is more exotic. PSR J2322265 Zerob might have formed through a process we don't yet understand, perhaps involving unique chemistry in the extreme environment around a pulsar. The intense radiation field, the powerful magnetic forces, the plasma environment, all of these factors could potentially drive chemical processes that don't occur anywhere else in the universe. Maybe the conditions around PSR J2322265 preferentially create carbon molecules while destroying or dispersing other compounds. Maybe there's some unknown mechanism that concentrates carbon and helium while excluding other elements. This is essentially admitting ignorance, saying we don't know how it formed, but sometimes that's the honest answer. And it's the answer that many researchers are leaning toward. Michael Zhang put it bluntly, it's very hard to imagine how you get this extremely carbon-enriched composition. It seems to rule out every known formation mechanism. But ruling out known mechanisms doesn't mean the planet is impossible. It means we need to develop new mechanisms, new models, new theories. And that's exactly what researchers are attempting to do. Roger Romani has proposed one intriguing hypothesis involving the planet's interior structure and evolution. He suggests that as PSR J2322 265 Zerobe cools, losing heat through radiation into space, chemical processes in its interior could be separating elements by density and chemical affinity. Carbon and oxygen might be present together deep in the planet, but as the interior cools, they crystallize in different layers. Carbon, being less dense than oxygen compounds at the pressures and temperatures in the planet's interior, might float upward, gradually, enriching the upper layers and eventually the atmosphere in carbon. Meanwhile, oxygen could be locked away deeper in the planet, perhaps combined with other elements into dense minerals that sink and remain in the core. As the companion cools down, Romani theorized, the mixture of carbon and oxygen in the interior starts to crystallize. This crystallization process could involve the formation of diamond layers, with carbon precipitating out of solution like minerals from cooling magma on Earth. Over geological timescales, this process could have enriched the outer layers and atmosphere with carbon, while depleting them of oxygen, creating the bizarre composition we observe. But even this clever hypothesis faces challenges. The timescales don't quite work out. For the interior differentiation to have proceeded far enough to create the observed carbon enrichment would require the planet to be relatively old, billions of years old. But the pulsar itself is a millisecond pulsar, which means it was spun up through mass transfer from a companion. This spin-up process should have occurred more recently, perhaps, only hundreds of millions of years ago. If PSR J2322 265 Zerobe is the remnant of that companion, or if it formed from material related to that process, it may not have had enough time for extensive interior differentiation to occur. Another factor to consider is the ongoing intense radiation and heating from the pulsar. PSR J2322 265 Zerobe isn't a cold, dead world quietly cooling in space. It's being actively bombarded with gamma rays and heated to temperatures of thousands of degrees. This ongoing energy input affects the chemistry of the atmosphere and possibly the interior. Chemical reactions that would normally occur slowly might be accelerated. Molecules that would normally be stable might be broken apart. The atmosphere might be in a state of continual chemical flux, with creation and destruction of molecules happening simultaneously. Some researchers have suggested that the atmosphere we observe might not be primordial at all. Instead, it might be a secondary atmosphere, continuously generated through processes occurring on and beneath the planet's surface. On Earth, volcanic activity releases gases from the interior, replenishing compounds like carbon dioxide and water vapor in the atmosphere. On PSR J2322 265 Zerobe, similar outgassing processes might be releasing carbon and helium from the interior, maintaining the atmospheric composition despite ongoing loss through evaporation. If this is the case, the planet's interior must contain substantial reservoirs of carbon and helium. But where did these reservoirs come from? And why are they dominated by these particular elements? Perhaps the planet's interior formed from material with an unusually high carbon-to-oxygen ratio, possibly related to the chemical composition of the pulsar's progenitor star or the supernova that created it. Or perhaps chemical fractionation processes during the planet's formation preferentially incorporated carbon and helium, while excluding other elements. The more researchers examine PSR J23222-265 ZeroB, the more questions emerge. Every potential explanation raises new puzzles. Every observation reveals new aspects that don't quite fit expectations. Maya Belesne, modeling the planet's distorted shape and orbital mechanics, found that the tidal deformation alone presents challenges for understanding the planet's interior structure. The lemon-shaped distortion indicates that the planet's interior must be at least partially fluid or plastic, able to deform under the pulsar's gravitational pull. But what material has the right density and mechanical properties to match the observations while also producing a carbon-helium atmosphere? The situation is further complicated by the retrograde atmospheric rotation, the atmosphere moving westward, while the planet rotates eastward. This decoupling between the atmosphere and the surface suggests that friction between them is relatively weak. On Earth, our atmosphere rotates with the surface because frictional drag couples them together. The air near the ground is slowed by friction with mountains, trees, buildings, and the ground itself. This friction transfers the Earth's rotation to the atmosphere, keeping them moving together. But on PSR J23222-265 ZeroB, something has broken this connection. The atmosphere has somehow detached and developed its own independent rotation, driven by temperature gradients and the complex interplay of heating and cooling as different regions face toward or away from the pulsar. This suggests that there might not be a traditional solid surface at all. Perhaps the planet's outer layers are liquid or semi-liquid, unable to exert significant friction on the overlying atmosphere. Or perhaps the atmospheric dynamics are so powerful, the winds so strong, that they overwhelm any frictional coupling with the surface. On Earth, even our most powerful hurricanes and jet streams are ultimately constrained by friction with the ground. But on a world with no solid surface, or where the surface is molten and unable to grip the atmosphere, the winds might be free to organize into patterns dictated purely by the heating and cooling cycles, creating a regime unlike anything we see in our solar system. Understanding this atmospheric behavior requires sophisticated computer models that simulate the flow of gases in extreme conditions. Researchers must account for the asymmetric heating from gamma radiation, the rapid orbital motion, the planet's distorted shape, the chemical composition of the atmosphere, and the ongoing evaporation from the outer layers. Even with powerful supercomputers, these simulations are extraordinarily challenging, and they often produce results that don't quite match the observations, suggesting that some key physics is still missing from the models. One factor that might be important is the pulsar's magnetic field. Neutron stars have phenomenally strong magnetic fields, and these fields extend out into space around them. PSR J23222-265 ZeroB orbits through this magnetic field, and the interaction between the planet's atmosphere and the pulsar's field could drive currents, create heating through magnetic friction, and potentially affect the atmospheric chemistry in ways that aren't yet, well, understood. Some researchers have suggested that magnetic effects might help explain the unusual atmospheric composition and behavior, but developing detailed models of these interactions is extremely difficult. What makes PSR J23222-265 ZeroB particularly valuable, despite, or perhaps because of, all these mysteries, is that it represents a natural laboratory for studying planetary processes under conditions we could never create artificially. The extreme environment, the bizarre composition, the ongoing destruction through evaporation, All of these factors make the planet a unique test case for theories about atmospheric chemistry, interior structure, tidal dynamics, and planetary evolution. By continuing to observe PSR J2322-265 Zerob and measure how it changes over time, astronomers hope to gain insights that will help them understand not only this specific object, but planetary systems generally. The James Webb Space Telescope will continue observing PSR J2322-265 Zerob, taking spectra at different orbital phases, measuring temperature variations across the planet's surface, searching for changes that might indicate atmospheric dynamics or ongoing evolution. Other telescopes will contribute observations at different wavelengths, building up a comprehensive picture of this impossible world. And theorists will continue developing models, testing ideas, proposing new formation scenarios, trying to find some combination of factors that can explain how PSR J2322-265 Zerob came to be and why it has the properties we observe. But PSR J2322-265 Zerob is not the only world that's forcing astronomers to rethink their understanding of planets. The universe, it turns out, is far stranger than we imagined, capable of creating planetary environments so extreme and so bizarre that they challenge our most fundamental assumptions about what planets can be. Other disturbing worlds. While PSR J2322-265 Zerob may be the most inexplicable planet the James Webb Telescope has observed, it's part of a growing catalog of worlds that disturb and confound astronomers in different ways. The universe, we're learning, has a much broader palette for creating planets than our theories predicted. Each new discovery reveals possibilities we hadn't considered, challenges assumptions we thought were solid, and expands our understanding of the diversity of worlds that can exist. Consider TOI 561b, an ultra-hot super-Earth located 280 light-years away in the constellation Sextans. This world represents a different kind of impossibility, but one equally disturbing in its own way. Like PSR J2322-265 Zerob, TOI 561b orbits extraordinarily close to its star, completing an orbit every 11 hours. It's about 40% larger than Earth, with roughly twice Earth's mass, placing it in the super-Earth category. Planets larger than Earth, but smaller than Neptune. The disturbing thing about TOI 561b isn't its orbital period or its size. We found many ultra-hot, close-orbiting planets. What's disturbing is that it has an atmosphere at all. The planet orbits so close to its star that its day side is covered in molten rock, a global ocean of magma with temperatures exceeding 3,200 degrees Fahrenheit. At this distance, exposed to intense stellar radiation for billions of years, the planet should have lost any atmosphere it ever had. The radiation should have stripped it away, molecule by molecule, leaving only bare rock glowing in the starlight. But when the James Webb Telescope observed TOI 561b, it found something unexpected. The planet's temperature was cooler than it should be, significantly cooler, by about 1,700 degrees Fahrenheit. The only reasonable explanation is that the planet has a thick atmosphere that's redistributing heat from the day side to the night side, and possibly reflecting some starlight back into space. An atmosphere on a world that, by all rights, should be airless. Johanna Teskey, the lead researcher studying TOI 561b, expressed the profound implications of this discovery. What's really exciting is that this new data set is opening up even more questions than it's answering. She said, The planet exists in a chemical environment very different from our solar system. It orbits a star twice as old as our Sun, formed in a region of the Milky Way called the thick disk, where the abundance of heavy elements is lower than in the Sun's neighborhood. It must have formed in a very different chemical environment from the planets in our own solar system, Teske explained. How has TOI 561b retained its atmosphere? The current hypothesis involves a delicate balance between atmospheric loss and replenishment. The planet's surface is covered in magma, molten rock that's constantly releasing gases into the atmosphere. Water vapor, carbon dioxide, and other volatile compounds bubble up from the interior, replenishing the atmosphere even as the star's radiation tries to strip it away. It's a dynamic equilibrium, with gases being added from below at roughly the same rate they're lost from above. The atmosphere itself is thought to be thick and volatile rich, composed of gases that don't exist in Earth's atmosphere in any significant quantity. Strong winds race around the planet, transferring heat from the perpetually lit day side to the eternal night. Silicate clouds made of vaporized rock, the same material that forms solid ground on Earth, may float in the upper atmosphere, reflecting sunlight and contributing to the planet's lower than expected temperature. The idea of clouds made of rock vapor floating through an atmosphere kept aloft by the constant outgassing of a global magma ocean presents a vision of a world so alien that it strains imagination. Raphael Luque, an astrophysicist not involved in the TOI 561b research, but who studies ultra-short period planets, pointed out the significance. We do not expect that an atmosphere can survive under such extreme irradiation, he said. The fact that it does means our models of atmospheric retention and loss need revision. What factors allow some ultra-hot planets to maintain atmospheres while others don't? How efficient is under what conditions does the balance tip toward atmospheric loss versus retention? Then there's WASP 107b, dubbed a super puff planet, which presents yet another form of planetary impossibility. Located about 210 light-years away, WASP 107b is almost as large as Jupiter, but contains only 12% of Jupiter's mass. Its density is so low that astronomers compare it to cotton candy, a planet that's mostly empty space, wrapped in a diffuse atmosphere that extends for enormous distances. What makes WASP 107b particularly disturbing is that it's losing this atmosphere at a tremendous rate. Observations with the James Webb Telescope revealed a massive plume of helium gas evaporating from the planet, streaming out into space like a comet's tail. The planet's atmosphere is essentially being boiled off, the lighter gases escaping into space so rapidly that the planet's appearance is changing on human timescales. Over millions of years, WASP 107b will lose so much of its atmosphere that it might shrink to a fraction of its current size. Vinyeshwaran Krishnamurthy, who led the research on WASP 107b's escaping atmosphere, called it the first time JWST has captured helium escape from this planet. The observations show not just that the atmosphere is escaping, but reveal details about the process, the velocity of the escaping gases, their temperature, their composition. WASP 107b is giving us a real-time view of a planet in the process of transformation, gradually losing the atmosphere that defines its current nature. And perhaps even more disturbing than individual planets are the planetary systems that seem to violate everything we thought we knew. Consider the planet hunters have found around PSR J0952 0607, a black widow pulsar that contains the most massive neutron star ever measured, 2.35 times the mass of the Sun. This finding itself is extraordinary because it pushes up against the theoretical upper limit for how massive a neutron star can be before it collapses into a black hole. The companion to PSR J0952 0607 is being systematically destroyed, eroded by the pulsar's radiation. It has been whittled down to only 20 times the mass of Jupiter, no longer a star by any definition, more like a very large planet or a brown dwarf. The side facing the pulsar is heated to over 6,200 degrees Kelvin, hotter than our Sun's surface. Over billions of years, this companion will be completely consumed, evaporated into space, leaving the pulsar spinning alone. Or consider the runaway planet, CHA 1107 7626, which represents another category of cosmic nightmare, a rogue planet that doesn't orbit any star at all, floating freely through space while somehow accumulating mass at a ferocious rate. This free-floating planet is eating up material at the rate of 6.6 billion tons per second, displaying behavior more characteristic of a star forming than a planet. It's as if the distinction between planet formation and star formation has become blurred, creating an object that doesn't fit comfortably in either category. Alice Almendros Abad, who studied CHA 1107 762, noted the implications. Our main motivation to study this kind of object is to understand whether these objects are former planets that have been ejected from their planetary system, or they have formed isolated from the gravitational collapse, like stars do. The answer matters because it determines whether rogue planets are failed stars, ejected planets, or something entirely different. A new category of objects that form through processes we're only beginning to understand. Then there are planets like those the Webb Telescope found around the star ZTF SLRN 2020, a system where a Jupiter-sized planet appears to have plunged into its own star, not through orbital decay or tidal effects, but in what looks like an act of cosmic suicide. The collision left traces, a ring of dust, around the star marking where the planet struck, and vaporized, ejecta from the impact, blown out into space. Because this is such a novel event, said Ryan Lau, the lead researcher, we didn't quite know what to expect when we decided to point this telescope in its direction. The discovery challenges our understanding of planetary orbital stability. Planets can migrate inward over time through interactions with other planets or through friction with gas in the protoplanetary disk during formation. But for a planet to spiral inward to the point of collision requires specific conditions that astronomers are still working to understand. The event is apparently rare. This is the first time we've observed clear evidence of it happening, but the fact that it happens at all suggests that planetary systems can be more unstable than we thought. Each of these disturbing worlds, PSR J232265 Zerobe with its impossible atmosphere, TOI, 561b with its improbable atmospheric retention, WASP 107b with its evaporating gases, the massive neutron star slowly consuming its companion, the rogue planet acting like a star, the planet that dove into its host. Each one challenges a different aspect of planetary science. Together, They're forcing astronomers to recognize that planets are far more diverse, far stranger, and far more capable of existing in extreme conditions than our theories predicted. The solar system, the only planetary system we could study in detail until recently, turns out to be remarkably orderly and well-behaved. Mercury orbits at a safe distance from the Sun. Venus, Earth, and Mars are all rocky planets with stable orbits and, in Earth's case, a life-supporting atmosphere that has persisted for billions of years. The gas giants Jupiter and Saturn orbit in nearly circular paths far from the Sun, serving as gravitational shepherds that stabilize the inner solar system. The ice giants Uranus and Neptune occupy the outer reaches, cold and distant but predictable. But as we've discovered, thousands of exoplanets orbiting other stars, we've found that the solar system is unusual, perhaps even rare. Most planetary systems we've detected look nothing like ours. Hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits the Sun, are common. Super-Earths, planets between Earth and Neptune in size, a category that doesn't exist in our solar system, are everywhere. Planets with eccentric, elliptical orbits that would destabilize our system are typical in others. And now, with the James Webb Space Telescope's unprecedented ability to study planetary atmospheres and surface conditions, we're finding that the chemical and physical conditions on exoplanets are far more varied than we imagined. Carbon atmospheres, magma oceans maintaining thick air, cotton candy planets losing their gases to space, worlds being cooked by dead stars. The universe's creativity in making planets seems endless. This diversity is both exciting and deeply unsettling to planetary scientists. Every new discovery is an opportunity to learn, to expand theories, to understand processes we never conceived of. But it's also a reminder of how little we actually understand. The models and theories that seemed solid just a decade ago are now being questioned and revised, sometimes torn down entirely and rebuilt from scratch. PSR J2322 265 Zerob, with its carbon-helium atmosphere that defies every formation mechanism we know, might be the most disturbing planet the James Webb Telescope has found. But it's part of a larger pattern of discoveries that are revolutionizing our understanding of planets, atmospheres, and the possibilities for worlds throughout the universe. What this means for understanding planets. The discoveries of PSR J2322 265 Zerob and other deeply unusual worlds have implications that extend far beyond individual bizarre planets. They're forcing a fundamental reassessment of planetary science, challenging assumptions that have guided research for decades, and opening up new questions about the diversity and evolution of planetary systems throughout the universe. For most of the history of astronomy, our understanding of planets was based entirely on the 8 worlds orbiting our Sun. We saw that rocky planets formed close to the Sun, where temperatures were high enough to prevent volatile compounds like water and methane from condensing. Gas giants formed farther out, where it was cold enough for volatile ices to exist, allowing cores to grow large enough to capture thick hydrogen-helium atmospheres. This frost-line paradigm seemed to explain why the solar system is organized the way it is. But the discovery of hot Jupiters in the 1990s shattered this simple picture. Gas giants orbiting closer to their stars than Mercury orbits the Sun couldn't have formed where we find them. It's too hot for them to have accumulated gas efficiently during formation. They must have formed farther out and migrated inward perhaps through gravitational interactions with other planets or with the protoplanetary disk. The recognition that planets can migrate significantly from where they formed was revolutionary and required rewriting planetary formation models. PSR J2322265 Zerob represents another level of challenge. It's not just that the planet is in an unexpected place, though orbiting a pulsar is certainly unexpected. It's that the planet's composition seems to rule out all known formation pathways. If it formed from a protoplanetary disk, the composition should reflect that disk's chemistry. If it's the remnant of a stripped star, it should show evidence of nuclear fusion products. If it formed through some alternative process, we need to identify what that process is and understand why it produces the observed composition. The carbon-helium atmosphere, with its absence of oxygen and nitrogen, suggests that either our understanding of stellar nucleosynthesis is incomplete, or our models of atmospheric chemistry in extreme environments are missing crucial physics, or some entirely new process is at work. Each possibility is disturbing in its own way, because it implies that fundamental aspects of astrophysics, aspects we thought were well understood, may need revision. One of the key insights emerging from exoplanet research is that planets are not simply passive objects that form and then remain unchanged. They're dynamic systems that evolve over time through complex interactions with their stars, with other planets, and through internal processes. Atmospheres can be gained or lost. Orbits can migrate inward or outward. Compositions can change through chemical processing. TOI 561b, with its magma ocean continuously replenishing an atmosphere that shouldn't exist, illustrates this dynamism. The planet exists in a state of active evolution, with material cycling between the interior and the atmosphere, a delicate balance maintained between atmospheric loss and replenishment. This challenges the notion that ultra-hot planets quickly lose their atmospheres and remain airless thereafter. Instead, we now must consider that some planets can maintain atmospheres through active processes, opening up new possibilities for which worlds might be habitable or interesting. The evaporating superpuff planet WASP 107b shows that some planets are in transitional states, actively changing on timescales that, while long by human standards, are geologically brief. WASP 107b will look completely different a million years from now, having lost significant amounts of its atmosphere. This raises questions about the life cycle of planets. At what stage in their evolution are the planets we observe? Are we seeing them in a stable configuration or in a temporary phase? How many planets that look one way now will look dramatically different in the future? The diversity of extreme planets also has implications for the search for life beyond Earth. For decades, astrobiologists focused on finding Earth-like planets, worlds similar in size, composition, and orbital distance to our own planet. The assumption was that life as we know it requires conditions similar to those on Earth: liquid water, a rocky surface, a protective atmosphere, moderate temperatures. The search for habitable planets largely meant looking for Earth analogs. But the more we learn about planetary diversity, the more we realize that Earth-like conditions might not be necessary for life, and that habitable might encompass a much wider range of environments than we thought. Life on Earth exists in extreme environments, in boiling hot springs, in ice, in the deep ocean, in acidic lakes, Earth life has adapted to conditions we once thought impossible for life. Could life exist in environments even more extreme than those on Earth? PSR J2322 265 Zerob is certainly not habitable by any conventional definition. The intense radiation, the extreme temperatures, the bizarre atmospheric chemistry all make it hostile to life as we know it. But studying such extreme worlds helps us understand the limits of what planets can be, and by extension, the range of conditions under which life might potentially exist. If planets can maintain atmospheres in conditions as extreme as those on TOI 561b, perhaps other planets can maintain habitable conditions in environments we previously thought were too harsh. The discoveries also highlight the importance of studying planets around different types of stars. Most exoplanet research has focused on planets around Sun-like stars because those are the most similar to our own system and because they're relatively bright and easy to observe. But the universe contains many more red dwarf stars, smaller, cooler, longer-lived than the Sun, and finding out what kinds of planets form around these stars is crucial for understanding planetary diversity. Pulsars represent an extreme case, stars that have died and been reborn as neutron stars. The fact that planets can exist around pulsars at all is remarkable. The supernova that creates a pulsar should destroy any existing planets and disperse their material. For planets to exist afterward means they either survived the supernova somehow, formed from material that fell back after the explosion, or formed from the remains of a companion star. Each scenario tells us something about how resilient planetary systems can be and what conditions are required for planet formation. The discoveries are also driving technological development. Each new type of unusual planet creates demand for better observing capabilities. To fully understand PSR J2322 265 Zerobe's atmosphere, astronomers need to measure its spectrum at higher resolution, observe it at different wavelengths, watch how it changes over time. This requires pushing telescopes and instruments to their limits, and increasingly requires building new instruments specifically designed to study exoplanet atmospheres. The James Webb Space Telescope, with its large mirror and infrared sensitivity, represents a huge leap forward in exoplanet characterization. But even JWST has limits. Future missions are being planned specifically to study Earth-sized planets around nearby stars, to characterize their atmospheres in enough detail to search for and to image planets directly rather than detecting them through indirect methods. Each generation of telescopes reveals new details and raises new questions that require even more advanced instruments to answer. The theoretical side of planetary science is also evolving rapidly. Computer models of planet formation, atmospheric chemistry, and orbital dynamics are becoming increasingly sophisticated, incorporating more physics and running at higher resolution. But the discoveries of planets like PSR J232265 Zerob show that the models still have gaps. There are processes occurring in nature that aren't adequately represented in simulations, either because we don't know they exist or because we don't know how to model them accurately. Bridging the gap between observations and theory is one of the major challenges facing planetary science. When a telescope reveals a planet with properties that don't match any model, is the problem with the observations or with the models? Often, it's both. Observations can be misinterpreted and models can be incomplete. Progress requires iterative refinement, with observations guiding theory and theory suggesting new observations. PSR J2322 265 Zerobe will continue to be studied intensively in the coming years. Astronomers will observe it at multiple wavelengths. Watch for changes in its spectrum that might indicate atmospheric dynamics. Measure its orbit with increasing precision to constrain the masses involved, and look for additional planets in the system that might provide context for how PSR J2322 265 Zerobe came to be. Each new observation will refine our understanding and, quite possibly, raise new mysteries. But beyond the specific scientific questions about this one peculiar planet, PSR J2322 265 Zerobe serves a broader purpose. It reminds us that the universe is stranger and more creative than we imagined. It challenges our assumptions about what's possible. It shows us that nature can create conditions and objects that strain our ability to explain them. And it invites us to keep looking, to keep discovering, to keep expanding the boundaries of human knowledge about the cosmos and the worlds within it. Conclusion. As we drift toward the end of this journey through cosmic strangeness, let's take a moment to reflect on what these discoveries mean, not just for science, but for how we see our place in the universe. PSR J2322 265 Zerobe, spinning around its dead star companion in an orbit that takes less than 8 hours. With its lemon-shaped form and its atmosphere of carbon, soot, and helium that shouldn't exist by any theory we've developed, this world represents something profound. It represents the limits of human knowledge, the boundaries of our understanding, the edge where what we know meets what we have yet to learn. There's something both humbling and exhilarating about discovering an object that doesn't fit our theories. Humbling because it reminds us how much we don't know, how far we are from a complete understanding of the universe. Exhilarating because it shows that there are still mysteries to solve, discoveries waiting to be made, questions we haven't even thought to ask yet. The universe is not required to make sense to us. It's not obligated to follow the rules we've written down in textbooks. Nature existed long before humans, will exist long after we're gone, and operates according to its own physical laws without regard for whether those laws are comfortable or comprehensible to us. When we discover something like PSR J2322 265 Zerobe, we're not finding an error in the universe. We're finding an error in our understanding, a gap in our knowledge, an opportunity to learn. And that's what makes these disturbing discoveries so valuable. Each one is a teacher, showing us where our models fail, pointing us toward new physics, new chemistry, new processes we need to understand. PSR J2322 2650b is disturbing precisely because it challenges us, forces us to think harder, to question our assumptions, to develop new ideas. But there's also something peaceful about these cosmic mysteries, something that invites contemplation and wonder. When you look up at the night sky, knowing that 750 light-years away, a planet made of impossible chemistry spins around a dead star, compressed and distorted and slowly being cooked away by gamma radiation, when you know that the universe contains such places, it puts our earthly concerns in perspective. Our planet, for all its troubles and complexities, is a haven of stability compared to these extreme worlds. Earth orbits at a comfortable distance from a stable star. Our atmosphere has persisted for billions of years, providing the oxygen we breathe and the protection from radiation we need. Our magnetic field shields us from cosmic particles. Our climate, while changing, remains within bounds compatible with life. We live in a cosmic oasis, a pocket of stability in a universe capable of creating environments so extreme that they challenge description. And as you drift off to sleep tonight, let these thoughts wash over you like a gentle tide. Somewhere out in space, PSR J2322265, Zerob continues its endless orbit, its strange atmosphere churning with soot and molecular carbon, its interior perhaps filled with diamond layers, its surface heated to temperatures that would vaporize rock. It exists whether we understand it or not, following the physical laws of the universe with perfect consistency, teaching us through its mere existence that there is always more to learn, always more to discover, always more wonders waiting in the darkness between the stars.